Hello, everybody, and welcome to another episode of Mathematics for Computer Science and Artificial Intelligence. Today, we will take another look at derivatives and its applications. Specifically, in this video, we will discuss linear regression. So, first we need to know what is a linear regression. And a simple definition of a linear regression is an approximation of a line that best fits a given data. So the linear regression is a parametric model, which means that it takes some parameters in order to predict something. Another definition for this would be a linear model that best fits a given data. This data could be thought of as training data. Now, let's take a look at this problem, right? So we are trying to estimate how much money we will make if we invest $1,000, $10,000 on a company C, let's just call the company C, on the 15th month and hold stocks for 3 years. We can use pure mathematics, but as computer scientists, we'd rather let the computer do all the work for us, right? So let's see, this is the data that we have collected. So this is the month. Also, you can think of this as the x-axis, and this is the stock price or the y-axis, right? So we have for the first month, second month. For some reason, we didn't collect data on the third month, but we collected on the fourth, on the 9th, 10th, and so on and so forth. And this is the price of the stock in each of these months. Now, if we graph this function, we can see that we have some sort of pattern that grows somewhat linearly, right? So if you think of a line right here, this is what the line would kind of look like. And this is what linear regression is good at. So if we want to ask the model questions that we don't know the answers to, but that should be based on the data that we have, we can just program or build a linear regression model that can predict future data. Say, for example, what's going to be the price on the 15th month or the 20th month or the 60th month or something like that, right? Or what was the price on the third month that we don't have here. So what we want to do is find out which are the what model makes this line as accurate as possible. So let's move on, right? So this is the equation of a line. And remember, we are trying to make a line, so we need to know what the equation of a line is. And then we have the slope, and we have the y-intercept. So if you remember, the slope pretty much is how fast the function grows or increases, or it decreases, how fast it increases, or how much it decreases. B is some sort of the y-intercept or the offset. So let's illustrate this in our tool Desmos. Okay, so we're in our tool Desmos here. We have a slider for M and we have a slider for B. Let's just see what the effect of each of these are. So if we increase B, we see that the line is moving up. As we decrease it, we see that it's moving down. So it's really the offset in the y-coordinate. When we increase M, we see that this function starts to grow. When we decrease it, we see that it starts to shrink or decrease. So M is pretty much how much the function is sloping. And is it sloping up or down? That depends on the value of M. Great. So now that we know that about the line function, right? What can we tell about this? Well, we know that the line is defined by its M and B value because X is pretty much our independent value. We don't want to change X to change the line, right? We want our M and B value to form a line for any X that is accurate enough to predict the right value in the data that we have. So for this, let's just see what our model, our data looks like. This is what we have so far, right? That's the same thing as in the previous spot. So what we need to do is find a way to tell how far off or how close we are to the actual line that best fits the model. So let me say it again. We want to find out how far or how close we are to the actual values in each point for each point of x that we have. So for that we define a cost function. So a cost function for a single point, let's focus on this point right here. Cost function for a single point would be what our model predicts minus the actual value. So the actual value for here, this is for the first month, is 50 cents. If our model predicts, let's say 63 cents, then we have 63 cents minus 50 cents, that's 13 cents, and then we square it. So we can define the total cost as the prediction for each point of x minus the actual value y of that particular x, so from here, squared, and then add them all together. This is the sum, right? This is summation. So the prediction of our model is really mx plus b. So we can rewrite this total cost as mxi, so the ith x plus b, which should be the same for regardless of the y value, minus the y value for that x value squared, and then just keep adding them together. So you might be wondering, why is this the cost function? Why this particular formula works? And first of all, we can see the subtraction element of it, which is just to measure the distance between one point and the other. So really what we want to find out is why we have to square it. And think about it this way. If we have an error in which the value is negative and we have one in which the value is positive, the total error could be low or could even be zero, when in fact we have some error. So we have to find a way to just maintain the magnitude of each error. So yeah, we could take the absolute value of each error, and in theory we would maintain the magnitude of the error. But actually the square works better. Why? Because the square can make the large errors even larger, and the small errors, meaning the errors less than 0 or less than 1, sorry, even smaller. So the square works very well for an error function. Now that we have defined our error function, what we want to do for a linear regression is we randomly initialize m and b. Let's just randomly initialize them to any numbers, right? So in this particular case, let's say that m is minus 0.15 and b is 0.78. So if we build the line for this particular function, now we have minus 0.15 x times x plus 0.78, and this is the line that we have created. Obviously this line is not representing the model very well or the data very well, so we want to adjust the m and b values so that this line could more accurately represent the data. This is what the linear regression is all about. Okay, so let's see, how are we going to do that? Well, let's first of all see what the total cost is. So this cost right here is represented by using this formula right here and seeing the error for that particular point. So this is the error for the first point. It's not too high. This is actually a pretty good error. This one's even better because it's closer to the actual value. So these two errors are not bad at all. But when you look at the other errors, you can actually see that they keep growing and growing. So the total cost, by the way, I'm using error and cost interchangeably. It's the same thing. It doesn't really matter which one you use. The total cost is now 11.6653. So this number right here is telling us how far off we are, and 11 is quite a high number when it comes to numbers such as 0.15, 0.52. Those are like really small numbers, so this is a relatively high cost. All right, so what do we want to do? Well, okay, so let's go into the Desmos tool and see how the error function could actually look. Great, so this is an example of how the error function could actually look. So remember that the error function is a quadratic function because it's to the tooth power, or it's a squared value. Remember, it's the prediction minus the y value squared. So we have some sort of parabola function that represents the actual error. Now we have the m and b function. This is by the way, this is not like the actual error function. This is just an example of how the error function actually looks, which is a parabola that's going up, right? It never goes into the negative side because we're squaring it, so we never have any negative values. So what we want to do is find where the error is minimum, so where the error reaches its minimum point. And if you remember on our previous discussion of maxima and minima, we know how to find the minimum or the minimum point for any function. How do we do that? We find where the slope is 0, or where the differential or the derivative of the function is 0. Now, what do we know about this function? We're not taking the derivative with respect to one variable anymore, because we have two variables that are actually affecting our error, which is m and b. Because remember, the x value and the y values are fixed. These are from our data set, so we're not allowed to change this. What we can change is the m and b value, so that we can minimize this error as much as possible. Now, if we want to do this manually, well, it's not that difficult, because we can just differentiate the function with respect to m and differentiate the function with respect to b, and then we can solve for m and b when each of the errors are 0, and then we can call it a day. Fine, that's not a problem. But remember, we are trying to let the computer do it for us, and with the computer it's not that simple. We cannot just say, oh computer, just solve for x when the error is 0. We have to do some neat tricks in order to make our computer get closer and closer to this point, just like this little circle that you see here, until it's so close that you cannot tell, until it's so close that it's like it's the minimum point pretty much. So you want to find a way in which you can minimize this function using some sort of magical computation power, some magical algorithm. And in fact, there is something very cool that we can use. So let's look at two examples, right? Either the error is high, and let's say that the m value, in this case, let's just imagine that this is graphed on the error or the cost in the y-axis and the m value on the x-axis. So in this particular case, if it's to this side, then we know that the m value has to be increased, right? So because the minimum point is at m equals 10. But if we're at here, the error is high, and the m value is less than what it should actually be. So what do we want to do? We want to increase the m value. But at this point, what do we notice about the slope? Remember, this is going down. Therefore, the slope, or the derivative of the function with respect to m, is negative. Again, it's negative. And if we want to increase m, what do we have to do? We have to subtract a portion of the error, not the whole error, a fraction of the error. Because if we subtract the whole error, what we will do is overthrow, and then we will be here and then coming back here. So what we want to do is just subtract a portion of the error, or a fraction of the error that we obtain for all given x values, or for the entire data set. So again, if we're on this side, the function is sloping up, or the derivative of the function is sloping down. So if it's sloping down, then it's negative. And if we have the m value, and we know that right now m is 9.259, and we want to get it to 10, we have to increase it. So we subtract a fraction of it. Now let's look at the other case in which we're in this side. In this side, we know that we want to decrease m because m is now 11, right? Or very close to 11, and we want it to be 10, so we want to decrease it. In this case, the derivative of the cost function with respect to m is sloping up, or is increasing. So we still want to subtract it, which is very convenient. So no matter where we are around the m value, whether we're at a value that is less than it should be or more than it should be, we still want to subtract a fraction of the slope, pretty much, so that we can get to the minimum point right here. And the same could be said for b. Just imagine that this is not m anymore and this is b. We know that the minimum point of the function is when b equals 10. So if we're before, we subtract a fraction of the slope of the b value, of the cost with respect to the b, and when we're in this side, we do the same thing. Great. So let's get back to our slides. Great. So now we know that we need the slope of the function with respect to m and the slope of the function with respect to b. I've already gone ahead and differentiated this cost function. It's actually very simple to differentiate when you use the chain rule. So with respect to m, remember that whenever we're taking the derivative of a variable with respect to the derivative of a function with respect to a variable, all the other variables become constants. So this is just how I obtained this particular derivative of the cost function with respect to m, and the same with respect to b. They're very similar, except that you could just say that the derivative of the cost function with respect to m is just x times the derivative of the function with respect to b. That's just one way to look at it. And if you look at this part right here, you can see that this is the square root of the cost function. But these are just different ways in which you can look at this function. This is just fine. Right. So now we defined this before, right? So the new m value would become the old m value minus a fraction. So we have mu. You can call mu this is a number greater than 0 and less than 1. So this is pretty much to just subtract a fraction and not the whole thing, not the whole cost. And by the way, if you look at this, this is big C, so this is not the cost of 1 point, but this is the whole cost. So the derivative of the whole cost with respect to m. Remember that the sum of the derivative the derivative of a sum is the sum of the derivatives. Therefore, the whole cost, the derivative of the whole cost function with respect to m is just adding the derivative of the cost function for a particular x value. It's just adding all of them together. So same thing for b. The new b value will be the old b value minus a fraction of the cost function or the derivative of the cost function with respect to b. Great. So now what are we going to do? We're going to build this table right here. So this table pretty much right now is telling us, well, we have the prediction that we had before according to our current m and b values that we had selected before, which by the way, we're going to select a learning rate of 0.001, which actually usually works very well. And we're going to stick to our old m values and b values. So what we have to do now is iterate. So for computer scientists, this would be like create a loop in which we can update m and b depending on their current value of their particular cost derivatives, right? So we have the total cost derivative for the actual m and b values right here. This is for the cost function with respect to m. for the derivative of the cost function with respect to m, and this is for the derivative of the function with respect to b. This is the actual cost. This is just to see how the cost is decreasing and decreasing as we update m and b. So I'll just go ahead and run a few iterations here, updating m and b, and you will see pretty much how it looks. So at this point, I've just run one iteration for m. So what I took is I took the old value of the cost function, or the derivative of the cost function with respect to m, and I used this formula right here to compute a new m value, and I updated it in the graph. So now you see that the predictions are pretty much a lot more accurate, and the error or the cost function is a lot lower. It's actually pretty low, 0.2809. So now let's run one iteration for b and see what we end up with. So after one iteration of the b value, the error decreased just a little bit more, or just a little bit. But yeah, the b value didn't change that much. That could indicate that it's actually very close to the value that it should be, whereas the m value was very far, and the majority of the error was due to the m value. So let's just run two more iterations and see what happens. So after updating the b value for the first iteration, we ended up with b being this number. It's actually very close to the actual number, but we have decreased the error or the cost a little bit more, which is what we're aiming for. So let's run two more iterations and see what we end up with. Okay, so after a few updating, this is still not the best model, but that's because we've only ran 2 or 3 iterations. So what we can see is that these functions, these derivatives or slopes, are getting closer and closer to 0. But as they get closer to 0, these values update by less, because remember that we're subtracting a fraction of it as per in the formula here. This is why doing this by hand would be tedious. This is why when we're doing this by hand, we solve this to be equal to 0. And when we are doing it this way with iterations, we'll let the computer do it, because of course the computer can do thousands of iterations in the time that we do one. Or actually the computer can do millions of iterations if that's the case in the time we do one. So what we will do after this in another video is that we will create a Python model for a linear regression, and we'll actually feed it this data set and see how well it performs, and if we can actually answer the question that we have before. So this will be continued in another series with our Python program. As always, be curious, ask questions, and try something out. If you have not seen the Python video and you actually want to try to model this with code, all you have to do is think a bit about the functions that we have, how you can program these functions, and then build a model that updates the m and b according to the actual errors that they produce or the slopes that they produce. So you can go ahead and try that on your own. Despite of that, I will upload the video and then we will keep going from there. Again, please leave your feedback. If you have any questions, please leave a comment, like the video if you did, and subscribe for more. My name is Brian Morphe, and thank you very much. You have a good one.